All right, let's jump right into this explainer and embark on a seriously exciting journey of creation. Today, we're taking a completely blank 2D screen and transforming it into a complex, real-world 3D manufacturing mold using SolidWorks. We are going to unpack the core philosophy of this incredibly powerful design software, taking you from the absolute basics all the way through to some truly advanced manufacturing techniques. So, let's get into it.
You know, there's a golden rule in CAD, and it comes straight from our source material today. The basic to make a good, solid modeling start from making good sketches. It's that simple. You absolutely cannot build a great 3D model without a flawless 2D foundation. If your sketch is flawed right out of the gate, well, your 3D part is ultimately going to fail.
We're going to move fast, but here's our roadmap for this explainer. 1. Setting the stage. 2. The 2D foundation. 3. Entering the third dimension. 4. Refining the model. And finally, 5. Advanced surfacing and molds.
Okay, Section 1. Setting the stage, the workspace. Let's establish the digital environment where all of our engineering magic actually happens.
Before you even think about drawing a single line, we have to lay down some ground rules. As our sources point out, you first need to define your units, like the millimeter-gram-second system, so you know exactly what scale you're working in. Next up, you choose a starting plane, whether that's the front, top, or right plane. But honestly, the most absolutely crucial step? You must always anchor your very first sketch to the absolute mathematical center of the workspace, the origin, at coordinate 0, 0, 0. This is what keeps your entire design grounded and predictable.
Section 2. Mastering 2D sketching. Now, what's really fascinating about this phase is that this is where we're drawing the literal blueprint for our future 3D part. Look, CAD software is notoriously full of jargon, but relations are simply the crucial rules that keep your sketches structurally sound. Think of them as geometric constraints that force your lines to be perfectly vertical, horizontal, perpendicular, or tangent to one another. Without these rules, your drawing might just collapse the second you try to adjust it. With them, it behaves exactly how you intend it to.
So the trick here is following a very specific 3-step order of operations to really lock down that design. Step 1, draw your basic geometric shape. And hey, it doesn't even have to be perfectly sized just yet. Step 2, add those geometric relations we just talked about. And step 3, apply smart dimensions. By giving your lines exact lengths and angles, you literally transform your design from a floating, underdefined blue blueprint into a rigid, fully defined black foundation. When those lines turn black, you know you're ready for the next step.
Section 3. Entering the third dimension. It is finally time to celebrate crossing over from flat lines on a 2D plane into physical 3D reality.
The absolute most fundamental tools to pull this off are the extrude boss and revolve boss. We use the extrude tool to just push a flat shape straight into the third dimension, instantly generating 3D mass and volume. It's kind of like a giant digital Play-Doh press. Revolve, on the other hand, takes a profile and spins it completely around a center line. This is exactly how you'd create cylindrical parts, like a water bottle or a mechanical axle, in just one smooth, sweeping motion.
Simple pushing and spinning is great, but it really won't work for organic shapes. So how do we actually solve for complex, winding structures that don't just go in a straight line or spin in a perfect circle?
Well, this is where the swept boss workflow comes in. It's pretty much the perfect solution for creating smooth, continuous pipes or custom pathways. It's a 3-parter. First, you draw your 2D profile, say a circle. Second, you open up a perpendicular plane and draw an intersecting path, basically the twisting track you want that circle to follow. Third, you sweep the profile right along that path.
But wait, what if the shape itself needs to change as it moves? The crucial point here is that a lofted boss allows a shape to organically morph. You draw multiple different 2D profiles spread across different planes. So you could transition from a circle on the bottom plane to a triangle right in the middle and up to a rectangle at the top. The software calculates the solid mass and organically blends it through all of those different profiles, giving you some incredibly complex geometry.
Section 4. Refining your 3D models. Now we're going to see how a designer acts less like a draftsman and a lot more like a digital sculptor, refining a raw 3D block into a totally finished, consumer-ready product.
The very first step in refinement is usually dealing with those sharp 90-degree edges. Adding rounded fillets and angled chamfers isn't just about making things look pretty, it is quite literally a mandatory manufacturing step. Sharp edges make parts dangerously sharp to handle, and in plastic injection molding, sharp inside corners act as stress traps that cause parts to just snap and break when they get popped out of the mold. Next up in our digital sculpting toolkit, we have patterns. Instead of manually redrawing a complex feature over and over, like a ventilation grill with 100 cutout holes, you just draw it once. Then you can rapidly duplicate those cuts using these powerful pattern variations. You can run them in linear grids, spin them in circular arrays, or even use curve-driven or coordinate table-driven patterns to map out highly specific designs. This saves a massive amount of time and guarantees perfect mathematical spacing every single time.
If you're designing a plastic consumer box, think of a TV remote control casing. There is a very specific three-step sequence you want to follow. First, you apply a draft, which means slightly angling the outer vertical walls so the plastic can physically slide out of the steel mold. Second, use the shell tool to hollow out the inside, leaving you with a nice, thin, uniform wall. Finally, you add internal ribs to give it structural integrity without adding the heavy, unnecessary weight of solid plastic.
Section 5. Advanced Surfacing and Molds. We built the bricks and mortar using solid mass, but now it's time to kind of break the rules of solid design to create really complex organic architecture.
Okay, prepare yourself for a massive paradigm shift in software logic. Up until right now, we've been using solid bodies, which have actual mathematical volume, mass, and thickness. But surfaces? They have absolutely zero thickness and no mass whatsoever. It's the ultimate digital diet. And because they aren't bound by the physics of solid volume, they have infinite malleability.
By manipulating these weightless boundaries, surface tools act exactly like a digital piece of fabric stretched tightly over a wireframe. You can just grab points and warp, pull, and bend this fabric in ways that solid metal or plastic, frankly, never could. This is exactly how industrial designers model those highly complicated aerodynamic swoops for sports cars, or the perfectly ergonomic asymmetrical contours you feel on handheld electronics. Once that outer surface shell is perfectly sculpted, you can then fill it in and transform it right back into a solid manufacturable body.
And this brings us to the absolute ultimate payoff of this explainer, using your finished design to instantly carve out a perfect manufacturing mold. The source material outlines this truly brilliant shortcut. Step 1. Assemble your finished 3D product totally inside a solid digital block. Step 2. Use the cavity feature to automatically carve out the negative space inside that block. Step 3. Simply split the block into upper and lower halves. Boom! You've got a perfect two-part manufacturing mold ready to go.
So you've seen a basic 2D blueprint evolve into a highly refined, complex 3D reality, all the way down to a physical manufacturing mold? Now that you really understand the underlying philosophy of 3D CAD design, what complex reality will you create the next time you open a blank 2D sketch? Jump in, open up the software, and start turning your own ideas into reality.